Hello guys, good afternoon all. So we continue a little bit on the type of deteriorations in the constructions, what we call material, from what we have left since our last class or our last meeting. So in our last class, we have already discussed about the corrosions in steel. So today we are going to discuss a little bit on the chemical attacks. Okay, so the chemical attacks actually it can be from three sources. One is from the acid, okay. One is from the acid. Another one is from the sulfate, okay, and another one is the alkali-silica reactions, which normally happens in the concrete. And so we will talk about all of this today, one by one. Okay, so at the end of the course, you should be able to understand the mechanisms of the chemical attacks, how these chemicals attacking our concrete, and then the factors that will influence the chemical attacks, and then also we will discuss on how to prevent or to mitigate the chemical attacks. Okay, and then the difference in terms of the acid attack, the sulfate attacks, and the AR attacks, which is the alkali-silica, alkali aggregate attack, or some other people call it as alkali-silica attack. Also, basically, they are the same things, and also the influencing parameters. Okay, so the durability of the concrete structure actually is determined by the rate of the concrete is decomposed as a result of the chemical reactions. Okay, so here we can see that the durability of the concrete is the rate of the concrete is decomposed due to the chemical reactions. So the longer time of the concrete it takes for the chemical reaction to happen, for the decompositions of the concrete, so which means that the concrete is more durable. Okay, and then the conditions for the chemical reactions to take place actually is with the presence of the water. So without the water, without the ingressions of the water into our concrete, so basically the chemical reaction or the chemical attacks into in our concrete actually can be totally prevented. Okay, so in general, the reaction between the aggressive substances and the reactive substances will take place as soon as these two things meet. Okay, they will take place as soon as the two things meet. But then sometimes we can only measure the durability of the concrete after many years, or even after 20 or 30 years. Okay, that is because the rate of transportation, okay, the rate of this chemical ingress, and this chemical ingress into our concrete, and it sometimes take many years for the sulfate, for the acid, or for the alkali to ingress into our concrete, and often it may take many years to show their effects, for example, like the crackings or the breakings of the concrete. Right, we will talk about that later on. And then the chemical reactions that leads to the decrease of the quality, it can be from three sources, like what we have already discussed earlier. The first one is from the acid, and no matter it is in the formations of the aluminum salts, and magnesium salts, or with the presence of the salt water. So it can damage our hardened cement. So that is the first one, acid. And the second one is the reactions from the sulfates, or in general, we call it as a sulfate attack. Okay, so the sulfate, it will attack our aluminate and our concrete. Okay, and the third one is the reaction of alkalis with the reactive aggregates in the concrete. So basically, it's the aggregate which contain a very high amount of the silica. Okay, so basically in the chemical attacks, there are three types. First one is the acid attack. So in the acid attack, okay, the actions of the acids on the hardened concrete is the conversions of the calcium compounds, no matter it is calcium hydroxide, calcium silicate hydrates, or calcium aluminate hydrates, to the calcium salts of the attacking acids. Okay, so it will form the hydrochloric acids, okay, hydrochloric acids, sulfuric acids, and also organic acids. So these three types of acids, three types of acid. So as a result, the structure of the hardened cement will be destroyed, and the rate of the reactions between the cement, the different acids with the cement is determined not so much by the aggressiveness of the acid. So no matter what types of the acids, be it hydrochloric, sulfuric, or organic acids, no matter what types of the acid, actually it doesn't matter. So the most contributing factor here, or the most influential factors here, actually is the solubility of the resulting calcium salt. So which means that the amount of the water presented in the concrete actually is the most important factors. Okay, so this is the schematic schematic drawing showing how the acid destroy our concrete. So the acid solutions, it can come from the environment, it can be from the industrial waste, acid, rain, and so on and so forth. When it enter our concrete, it will result in the conversions of the concrete layer by layer to form what we call a soft concrete. So this soft concrete, it will dissolute, okay, and then it will come out from the concrete. So a concrete which is attacked by the acid, normally it can easily be determined, or you can easily see the concrete which has already been attacked by the concrete through its surface only. The surface of the concrete which is severely being attacked by the concrete normally will have the very not rough surface, because you will see that when the concrete is leaching out from our concrete, the surface of the concrete will be very rough because of the protruding aggregates. Okay, we will talk about that later on. So magnesium and ammonium salts will react in the same manner as the equivalent acid. So the ammonium chloride will react as the free hydrochloric acids, and the ammonium nitrate as the free nitric acids. So be it magnesium or ammonium salts, they can react similar like acid, be it free hydrochloric acids or the free nitric acids. So this is not acid, this is the attack from the magnesium and also the ammonium salts with the presence of the soft water. Okay, with the presence of the soft water, and the result is the destructions of the hardened cement. So this is what, if you look at this picture, this is what we are talking about. So you can see that the aggregate is protruding from the surface of the concrete after being attacked by the acid. Because part of the part of the concrete has been dissolved, okay, and is leaching out from our concrete body. So actually the Portland cement is not acid resistant, okay, it's not acid resistant in nature, and the acid attack may remove part of the said cement, resulting in this very rough surface of the concrete. Okay, very rough surface of the concrete. And then the acids are formed by the dissolutions in water of carbon dioxide and also sulfur dioxide from the atmosphere. Okay, it can be from the industrial waste and so on and so forth. Right? It can also be from other source. All right. So in order to prevent this from happen, or to prevent your concrete from being attacked by the acid, so we have to ensure that your concrete is very dense. Okay, so that it can prevent the ingredients of the external agent to go into your concrete. So it can provide adequate cover. Okay, and sometimes in some extreme cases, sulfate resistant cement should be used if necessary in order to avoid this. So this is what happens, okay, when our concrete structure is being attacked by the acid. You can see this is the example of a floodgate, okay, because of the very humid environments, okay, and then the chemical inside this floodgate, it has already been severely corroded due to the acidic water. And so you can see the surface actually has already been leached out. Okay, so that is acid attack, a brief about acid attack. So now we move on to the sulfate attack. So sulfate attack, it is quite different compared with the acid attack. Acid, when it attacks the concrete, so basically it attacks entire concrete. Every component in the concrete, but sulfate attacks, it only attacks certain component of the concrete, or in particular it's only attack the tricalcium aluminate or the aluminate in the cement. Okay, so sulfate, it only attack the aluminate. So sulfate, when it contact with the tricalcium aluminate inside the cement, it will result in the formations of calcium aluminoferrite, or what we call as ettringite. Okay, so this is the product. So this is the product of the sulfate attack. Okay, it's what we call, scientific name is calcium sulfur aluminate, but we normally call it as ettringite. So this ettringite is the product of the sulfate attack. Okay, it's the product of the sulfate attack. So sulfate actually are present in most cements and also some aggregates. So we cannot avoid this. We cannot avoid this. But what we can avoid actually is we can prevent the sulfate which is coming from the soils, groundwater, seawater, industrial waste, and also from the acid rains. So how to do that? So we will talk about this later on, right? So the products of the sulfate attack on the concrete will occupy larger space. So the attringite, when the sulfate, it enter into our concrete, and when it is react or in contact with the 3-calcium aluminate, it will form attringite, and this attringite occupy larger space. It is much larger compared to the normal hydrated cement. Okay, and then it will cause the concrete to break when it expand. Okay, and then when the concrete is disintegrated and the cracks has already been formed, the steel corrosions can begin. For this part, you can refer back to our previous video for the corrosions of the steel. And then sulfate resistant Portland cement should be used where sulfates are present in the soil, water, and atmosphere when we expect this will happen. Okay, so sometimes a super sulfated cement, which is made by the surface slag, although it's not widely available, it can be also used in the highest concentrations of the sulfates environment. Okay, and sometimes we can also use the combinations like, for example, OPC plus the slag or pozzolan or the slag, which is as high as 65%, 70% in order to ensure that our concrete is well protected by the sulfate attack. So this is what happened when your concrete is being attacked by the sulfate solution from the environment. We have already talked about the sources. When it ingress into our concrete, okay, so ingress in our concrete, it will in contact with the hydrated 3-calcium aluminate, which is C3A. Okay, to form the attringite. So this attringite, it will expand. Okay, it will expand and it will result in crack. So when this crack, the link together, okay, it will result in disintegrations of this part of the concrete. Okay, this part of the concrete. And if you, let's say, if you have a rebar, if this is a RC, reinforced concrete, when you have a rebar here, your rebar will expose, and then your rebar will in contact with the oxygen and also with the moisture will result in the steel corrosions. Okay, and even your steel rebar is not what we call corroded. The sulfate attack concrete, the sulfate attack concrete will result in a lot of crack, as what you can see in this picture. Okay, it will expand. Okay, it will expand, it will deform, and it will result in a lot of crack. So the main influencing parameters for the expansions to happen is the exposure conditions, which is it's determined by the severity of the attack. So normally it's by the amounts of the aggressive substances, the chemical substances. Okay, and then we know that the chemical that happen, the chemical reactions happen here is the sulfate and also the C3A. Okay, the aluminate. Okay, the sulfate and the sulfate. So the severity of the attack is actually based on the amounts of the sulfates, and also the amounts of the 3-calcium aluminate. Okay, so we have to remember this. All right, and the second one is the accessibility, which is determined by the permeability of the concrete itself. So the dense of the concrete, sometimes people say that it is a more durable concrete. That is because it is less permeable. Okay, it can block portions of the sulfate to ingress into our concrete. Okay, and it is the rate of the transportations. Okay, the rate of the transport. So the denser is your concrete, the rate of transportations will be slower. Okay, and the sulfate actually will be harder to go into your concrete. Okay, and the third one is the susceptibility of the concrete itself. So let's say if your concrete is made by the cement, which has the high content of the C3A. Okay, sorry, C3A. So there is a higher possibilities that your concrete will be attacked by the attringite. More attringite will be formed. Okay, and of course with the amount of the water available. Okay, so this is what happens when your concrete structure is attacked by the sulfate attack. Okay, or the sulfate agent. Okay, it can break your concrete. Okay, it can break your concrete like this. Under very severe conditions. Take example when your concrete is an offshore structure. Okay, your concrete is an offshore structure. So this is what happened. So when the sulfate has already attacked your concrete, so sometimes sometimes it will result in a lot of cracks. Okay, and then like I said, it can result in expansions. Because of the cracks, and the volumes will also expand, and it will result in the upforce like this. Okay, so that is the what we call the effects, from the sulfate attacks. So we can protect our concrete against a sulfate attack by two measure in general. So the first one is by ensuring the sufficient degree of impermeability. So the denser the concrete, the harder the sulfate to get into your concrete. Okay, so I think that is basic. And the second one is, like I said earlier, the ethylene jet actually is from the sulfate. If we block the sulfate to go into our concrete, so that is the impermeability. Okay, that is impermeability. And then the concrete itself, or the cement itself, it should be have this very low content of the C3A. Okay, so if you are using the very low content of the C3A cement, so normally it is more resistant to the sulfate attack. Okay, so the fundamental difference between the attack of the acids and the attack of the sulfate actually is quite different. So like what we have already mentioned multiple times earlier, the acid, when it attack our concrete, actually it's react with all components in our cement. So on the other hand, the sulfates only will attack or will react with the C3A components in our concrete. So that is the difference. So if we look at here, if we compare the acid attack and the sulfate attack, actually the permeability of the sound concrete is less important for the acid attack. Okay, but it is very important in terms of the sulfate attack. So what about the exposure conditions? The exposure conditions is quite varies with the presence of the constituent other than sulfate. And so take example. So a moderating influence of chlorine ions will caused by the preferential formations of the chloroaluminates, which is what we call as radiosols, will not lead to detrimental expansion. So if we take into these considerations, take example like seawater, which is normally classified as a highly aggressive environment. So according to its high sulfate content, it is only moderate in the aspect of the acid content, or in the aspect of the acid attack. So that is the influence of the exposure conditions. And then what about the accessibility of the concrete? So the degree of the impermeability needed for the concrete to be sulfate resistant actually can be expressed by limiting the values of the depth of the water penetrations over the fixed periods of time. So in other words is that the more water inside our concrete, so it is more likely your concrete will be damaged by the sulfate attack. Okay, so in practical, how are we going to ensure the sulfate attack in the concrete is minimized is by translating it into a limiting value of the water cement ratio when we are designing our concrete. So we have already discussed this actually in our mix design, so you can refer to our mix design concrete mix design video. Okay, so in that video actually we have already discussed when we are designing for the durability of the concrete, actually we have to limit the values of the water cement ratio of the concrete. So that is the reason. And then the third factor is cement types. Okay, so if according to the definitions from the ASTM, we limit the aluminate or the C3A to a maximum of 8%. For a moderate sulfate resistant cement, and also to a maximum of 5% to a high sulfate resistant. And even in Europe, so normally they will limit to 3% of this C3A for high sulfate resistant. Okay, so recent research also has shown that the OPC when it is replaced, with slag, it is very good in terms of the sulfate resistant. Okay, so we can add slag in our OPC as much as 65% for a very high sulfate resistant cement. Okay, so in the cases of the combined attack, when your concrete is expected to be attacked by the acid combined with the sulfate, so the other factors may also influence the choice of the cement. So why is this happens? So take example, for low alumina Portland cement, alumina Portland cement, it is very good. Low alumina Portland cement, like what we have already discussed earlier, low alumina Portland cement, it is very good in terms of the sulfate resistance. But however, low alumina Portland cement is resulted or will resulted in the highest permeability towards chloride ion. Okay, towards chloride ion. So those are the things that we have to take into considerations when we want to design a durable concrete. So this is what happened. We have already talked about this in our previous video, which is pozzolanic reaction. So when the cement is in contact with water, you will have the hydration process where you will produce the CSS gel and also calcium hydroxide. So this is the main things, calcium hydroxide. So pozzolanic reaction is when we add pozzolans or the slag into our mix. The pozzolans, it will react with the calcium hydroxide to form calcium silicates. Okay, more what we call calcium silicates, which is the CHS gel, and then it will create it, or it will result in the denser concrete. Okay, so that is why when we add slag into our concrete, it can result in the better sulfate resistant concrete. Okay, so that is about the acid attack and also the sulfate attack. So now we move on to the alkali-silica reaction. So alkali-silica reaction, so some other people also call it as the alkali aggregate reaction. Okay, so why this happen? Because alkalis, actually it is come from the potassiums and magnesiums, which is from the water. Okay, which is from the water, but the silica actually is coming from the aggregates. Okay, so sometimes when we mix our concrete, we have to use aggregates, right? So some of the aggregates that we use contain a very high amount of the silica, and that actually is the reason that this alkali-silica reaction happened. So if you still remember in our previous class, actually we have already discussed about the typical what we call a typical failure mode of the concrete. So let's say if you have a concrete and then you have aggregates inside. Okay, so when we compress the concrete, so normally what will happen is that the interfacial transition zone will break. Will break at the first place. Okay, they will crack. Okay, they will crack at the first place. So if we compress this concrete further, so this crack will link together. Okay, and then up to the failure. Okay, it will break like this. But from here, actually, we can see that the aggregates will not fail, even up until the failure or the ultimate failure of the concrete, because the aggregate actually is the strongest component inside the concrete. But what happened in the alkali-silica reaction is that when your aggregates, so this is the aggregate, when your aggregates contain very high content of the silica, so when it is in contact with alkali, it will form a thing which is what we call as alkali-silica gel. So this alkali-silica gel, it will absorb the water from the surrounding, and then it will expand and it will break our aggregate. So this is the thing that we don't want it to happen, because the aggregate, which is the stronger part inside our cement, to fail first, even before the cement paste has failed. Okay, so that is what alkali-silica reaction. So if according to the BS 8110, it's stated that the alkali-silica reactions will only happen when we have the alkali, sufficient amount of alkalis in the pore fluids, which is the potassium and also the sodium. Potassium and sodium. Okay, and then the second condition is the sufficient amounts of the silica present in the aggregate. Okay, so if we do not want this happen, we have to what we call, if we want to prevent this from happening, we can avoid to use the aggregates which has the high content of the silica, and then also the sufficient amount of water where the alkali-silica reaction will absorb this water and expand. So without any of these things, the alkalis or silica or the water, the ASL will not happen in theory. Okay, the silica will not happen in theory. So there are normally two processes for this ASR. So the first one is the alkalis reacts with the aggregate in order to form the alkali-silica gel, like what you can see here. And then it absorbs the moisture by the gel by the osmosis and cause the expansions and leading to the crackings. Okay, so if you look at here, yeah, this is the schematic drawings showing the cracking resulted from the alkali silica reactions, and the shape of the cracks normally is indirectional. There is no directional, but you can determine whether the cracks of the concrete is due to the alkali silica or not can from this shape, which is normally as a star shape. Okay, normally as a star shape. So this is what happened. Yeah, this is normally it happened. We call this as a star shape or map crack. Map crack. So the microscopic picture showing the formations of the silica gel and the network of the crack arise due to the alkali silica reactions. So if you look at this picture, this is the alkali silica gel. Okay, so when it absorbs water, it will expand and it will give pressure inside our concrete and resulted in a lot of these fine cracks. Okay, and this is a picture showing the cracks through the chert aggregate. Chert aggregate, which is a sort of a sedimentary rocks due to the alkali silica reaction. So if you look at here, the aggregate has already breaks, cracks, okay, due to the expansions of the alkali silica gel. So the main parameters influencing the expansion in practice are the reactivity of the aggregate, no matter it presents in terms, in the forms of amorphous or crystallized silica, okay, and then the amount of the reactive aggregates that we use, and the third one is the calcium and the and the alkali concentrations happens in the pore water, and then the types of the cement that you use, the exposure conditions, and the amount of the water available. Okay, so in terms of the exposure conditions certainly play a very important role and may be responsible for a great difference in the rate of the deteriorations of the concrete. Yeah, for the concrete design, actually, the judgment of the aggregate is based on the test results at constant and high humidity. Okay, and we also know that if your concrete or your aggregates, yeah, will be undergoing the intermittent drying and wetting effects, okay, or this some sort like a cyclic load, it may lead to a greater expansion. So how are we going to retard or even prevent the progressing deteriorations? It's actually, it can be done through waterproofing the concrete, right? So some of the options for the repair and remedies, we have the coating like treatment, for example, like surface coatings using the sealants and siloxanes, and also we can saturate our concrete with lithium-bearing solution. So when your concrete is fully saturated, so it is very hard for the external agents, for example, like the acids or sulfate, or even the alkalis from the potassium and sodium to enter into your concrete, right? We also can strengthen our concrete or concrete structure when the concrete has already been deteriorated, where the load-bearing capacity has already been reduced, right? So by strengthening, for example, like this, and using the confining method using the FRP, right? It can restore the loading capacity of the concrete or the structural elements, and we can also add additional props like this, additional support system. Okay, so I think that will be all for today. See you again in our next class. Thank you. Bye bye.